All right, so we're going to start in with number 3. Who is it who needs number 3 so I know who to pay attention to?
Right here.
Okay. All right, I'll pay attention to this side of the room.
Wait, right here, me too.
Well, you're in that line of sight.
Okay. Everyone.
Well, no, this side didn't need it, so I'll focus my attention over here. No, I just want to know who to look, because it gets really frustrating. It's like I'm asking questions, I'm looking over here, and I'm getting nothing but flashing plans. So I know where to look now to get answers.
Let's go. That's up. 9%. Oh, it's okay, guys.
It's okay.
It's fine.
Okay, chemical reaction requires this much energy input for it to go. What is the increase in mass of products over the reactants? So, what, number 3? For your why, probably your biggest understanding you should have had in there was that matter and energy are the same stuff. And that matter, which is of course measured by mass, is a very concentrated form of energy. Now, probably these whys are going to help you the most on your evaluation of relativity, which is tomorrow. So, be good to make sure you understand these. That's when you have the relativity cartoons, which are going to be your evaluation of relativity. But they're not going to be numerical, they're going to be conceptual, like the whys. So, Alright, so we need our equations. Here they are. And we need the mass and energy equivalents. Well, I'm kind of in the middle of something. Can we talk afterwards?
Yeah.
Okay. So let's see. They give me energy, I think, in this problem, right? 4.02 times 10 to the 4th joules. That would be E stands for energy. And they asked me to find the mass, and I know the speed of light. Done. So let me know if you need help with the individual math. All right, so on to number 1. Momentum of a proton traveling at 0.88 c. So, things that you should know for your why. Things like speed of light is constant from all frames of reference. Momentum is relative, since both inertia and speed are, not speed, velocity, are relative. Of course, relative means they are different based on your frame of reference, right?
Yes.
So, and then let's see, let's go flip to our how, and we need the equation. It's right there for momentum. And since we're looking at different frames of reference, we need to grab the Lorentz transformation also. And let's see, what type of object we're looking at here? Proton. So it'd be good, you could flip to your facts and constants and everything sheet, and you could grab the mass of a proton. Right there. And that's the amount of matter a proton has when it's at rest. So it's right on the back of your rubric sheet. So let's see. You're looking for the momentum. You know gamma because this frame of reference is moving at 0.88 C. And so you know gamma. Check. Mass, the rest mass is the M right there. And U is how fast the object is moving from this frame of reference. And that would be the 0.88 C again. So, all you gotta do is plug in. And you got it. All right. Can I stop recording? Okay. All right, so let's look at number 2. Number 2, you have a particle, and you're asked when its momentum doubles. If it had from when it's traveling at 0.22 C. The Y for this is going to be absolutely identical to last time. So, reference number 1. And then equation sheet wise, let's see. We're changing frames of reference, so we want our Lorentz transformation. We're talking about changes in momentum, so we need our momentum equation. And that's it. So, this one. And then this one. And one thing we're told here is that the momentum at this new one, I'm going to call it momentum new, compared to the momentum at 2.2, wasn't it 2.2? Whoops. Okay. Yes, at 2.2 C, I'm asked to double mine. So that means my new momentum will be 2 times momentum at 2.2. Oh, it's 0.22, isn't it? So we'll just call it 2.2. How about that? Whatever you would like to do, Peter. Yep. So over here, the momentum at this new one would be the rest mass times whatever the new speed is, which I'll call V sub n for new, over the square root of 1 minus V sub n over C quantity squared. That's going to equal whatever. Guys, I'm having a hard time hearing myself, so you could down a little bit. Same on the other side, except I have this 2 in front of it. And of course, I know what the velocity is. And really what I want to end up solving for is Vn over C. So I'd like, remember, Vn equals some number times C. And really what I want, if I find Vn over C, then I get this number, and that's what WebAssign, that number is what WebAssign's asking for, right? They want Vn in terms of C. So, doing a little bit of algebra, right? The AMOs cancel out, which is kind of nice. I want to get Vn over C, so I'm going to take and I'm going to multiply each side of this by 1 over C. And what that'll do is over here give me Vn over C over square root of 1 minus Vn over C squared equals 2 times, now this is 0.22C over C, which is 0.22, over the square root of 1 minus, and this is that same thing, 0.22 squared. And at this point, it's just unpretty algebra, right? So what I would do is say, okay, well, if I take Vn over C and I say, now I'm going to call that X, then I would put all of this into either solve it by hand, solving for X, or put it into like Wolfram or something and solve for X. All right? Yeah, because all the right side's a number anyway. Yes, ma'am. All right, so number 4, how many grams of matter will be totally destroyed to run a 105-watt light bulb for 1 year? Couple good review things in here is reminding yourself what power is, right? So in your Y here, you definitely would want to remind yourself that power is the rate energy is used. The relativistic. Now I'm just checking. You guys. Okay. But you're paying attention, right?
I have to
All
think
right.
of my lip.
And the relativistic idea here is, of course, like our first one, leave it alone, that matter and energy are the same stuff. And do we expect a lot of matter to have to be used, or kind of a normal amount, or a little bit? Normal? You going normal? Very little matter will need to be. No, remember our discussion yesterday about it's very, very condensed, so very little matter will be needed. So there's a reinforcement on that. That's not that much. Okay. You can always copy a blank part. All right, so probably the other equation that you may or may not need to grab, but we can grab, back here with energy, and remembering that power is energy per time. So rather than grabbing that, I'm just going to write it. The power is energy per time, and what you really want to be careful of is make sure that your units align, right? Because your power, like, mine is what, 105 watts, which is 105 joules per second, but I'm given a time of 4 years, and years and seconds don't align. So I either need to change power into joules per year, which I could do, or change 4 years into how many ever seconds it is, right? So you can do either way, but you can't. If you take joules per second and equivalent, make it equal to years, it's not going to work. You're going to be off unit-wise. You're going to get these really funky units of joule years per second, which makes no sense. And then, of course, the energy you're using is from the matter, so you're using the energy equivalents in there for E. And then the other mistake a lot of people make is you come up with an answer of M equals 9732 times 10 to the negative fifth, and it would be in kilograms. I made up that number. But if you look here at the question, they ask for it in grams. So you have to make sure that you convert from kilograms to grams for your final answer. All right? You want it in grams, not kilograms. All right? So make sure that your time units agree. Make sure after you find it, it's going to be in kilograms if you go with seconds and joules. If not, it will be in funky units. And then convert that kilograms to grams.